Yeah, good afternoon, one and all. Good afternoon. Hi, Soumya. Hello.
Hello.
Good afternoon, ma'am.
Good afternoon, madam.
Good afternoon, sir. Good afternoon, one and all. This is Josna Devi Bodapati, Assistant Professor, Department of CSE, Vignas Dean to the University. As part of our endeavor to connect R&D professionals and academicians across the country, the department came up with these free online webinars on recent technologies for faculty, industrial professionals, researchers, and students. We have invited the eminent researchers from academia, industry, and R&D organizations who are working actively on the recent technologies like machine learning, artificial intelligence, big data analytics, and blockchain technologies. So as part of these series of webinars on 30th of August, so most of you have attended that webinar. So we had a webinar on evolution of ANN architectures by Professor Baya Yajnanarayan garu. So he's a retired professor from IIT Madras and he's currently working as an IRSS scientist like in Hyderabad. And his talk was on was very exploratory, and participants came to know the various details about like various kinds of architectures, right from the perceptron to the recent development of LSTM architectures. And respected participants, faculty colleagues, and my dear students, so it gives me immense pleasure to welcome you all to the second webinar on natural language processing and application perspective. And we have Dr. SOWMYA S. Sundaram with us. So welcome, SOWMYA, to the webinar.
Yeah, hi.
Thank you. So natural language processing is a subfield of artificial intelligence that assists computers with understanding of human language. Utilizing NLP, machines can understand unstructured information and helps humans to gain significant insights. NLP helps resolve ambiguity in language and adds useful numeric structure to the data for downstream applications like speech recognition, language translation, interactive chatbots, and text analytics. So now I request Dr. D. Venkatesulu, head of the department CSE, to speak a few words on this occasion. Sir, HOD sir, can you speak?
Yes.
Yeah, thank you, sir.
Good afternoon, everybody. Welcome to Dr. SOWMYA Sundaram. So it's a very happy note that you completed your PhD from IIT Madras. So I'm also alumni of IIT Madras. I completed 20 years ago under Professor Timothy Gonzalez. So I'm very happy to see you here, and on behalf of Vignans University Department of Computer Science and Engineering, we thank you very much, madam, for accepting our invitation to deliver a webinar on natural language processing and application perspective. I'm sure that all of our faculty members and also the faculty and the people working in industry will enjoy your talk for the next 1.5 hours. So thank you very much, madam.
Thank you. It's my pleasure.
Thank you, sir. Thank you for your words. So now it's my pleasure to introduce today's speaker, Dr. SOWMYA S. Sundaram. So I first of all, I would like to thank Dr. SOWMYA for accepting our invitation. Actually, within a short span of time, so she accepted our invitation and she made it possible to this webinar to happen. Dr. SOWMYA S. Sundaram is a PhD. She received her PhD from IIT Madras. Her research interests include natural language processing, knowledge representation, and fairness in AI. Currently, she is pursuing a postdoctoral fellowship at L3S Research Center, Germany, where she is working at the intersection of bioinformatics and NLP. So now, SOWMYA, so I hand over the session to you.
Yeah. So, hello. Thank you for giving me this opportunity. And I'd like to start off. So, the idea is to talk about natural language processing, what are the various applications, and to give a bird's eye view of the technologies that are there. Natural language processing is a very vast field. So, in this short format, I'll be trying to touch upon various aspects and various tools that are available And mostly I'd like to motivate what makes this field very interesting and why there is a lot of research happening in this area. So that is the overview, and I have kept this as less technical and as approachable as possible. And if you have more questions and if you need more technical aspects, we can discuss this after the presentation. So let me get started. So first, before starting with natural language processing, I'd like to talk about what constitutes intelligence and what we perceive as artificial intelligence as a consequence of that. So when we talk about intelligence or human intelligence, many scientists have categorized certain areas as what would contribute towards intelligence. Some of these ideas are representation. The complex ways in which our brain represents concepts is what leads to us human beings creating intelligent decisions. The second aspect is reasoning, where we manipulate these represented concepts and make some implicit information explicit. For example, if I have represented two concepts as apple and orange, and I know that both are types of fruits, then I should be able to infer some other element, say that a banana is a fruit, and I would have more rules for that. So these kind of reasoning aspects also include intelligence. Then we have perception. So perception and action go hand in hand, where we perceive the environment through our sense organs and we act accordingly. So perception and action has led in the field of artificial intelligence to robotics. Finally, the interesting part of language is there. So development of language for communication has helped human beings to uh, develop complex ideas and communicate these ideas, and allows exchange and transfer of information. With starting with the rudimentary sign language, we have come up with such complex linguistic languages, and it is indeed a measure of intelligence. So in artificial intelligence, we try to capture some or many of these aspects in the research. So coming to artificial intelligence, we have many sub areas. Traditionally, there was a lot of focus on problem solving, where you have a particular problem and an exponential space of solutions, and we are trying to figure out what the answer is. Next, a more complex field of knowledge representation developed. In fact, it was a knowledge representation where concepts such as frames and inheritance were first introduced, that was adopted by the object-oriented programming paradigms. So we can see that research was hand in hand. It is not like now we speak of artificial intelligence in everything, in every possible technology, from our mobile phone to our research. But it is interesting to note that this research started almost in the 1940s and 50s, along with the first computer, because humans in general are extremely curious about the limits to which we can push computer research and technology. Then, with the advent of more data, we moved into the machine learning paradigms, where we use the data to develop algorithms. We'll be talking about this later on, and as you've already had an introduction to artificial neural networks, I'll just touch upon it briefly before going into the language aspects of AI. Finally, we come to the perceiving and acting part, where these two fields of perception, that is computer vision and natural language processing, have become highly popular today. And its derivatives, for example, speech processing. This is because of the advent of deep learning, on which we would be talking subsequently. So before we get started, I'd like to talk briefly about the Turing test, where we are trying to identify whether a certain program is a human or not. So typically, this is a chatbot where you have many questions and answers, and you are trying to figure out whether that particular that particular set of questions and answers is being generated by a human being or a computer. Now, in the early version, so this is an annual competition with a huge prize money, and this competition in its early phases was defeated very easily when the human asked questions like, what is the 23rd square root of a huge number? In that case, then if the computer immediately responds to that, it is very clear that it is a computer and not a human being. So these are the kind of nuances that is there in natural language understanding. We have many aspects where you have to deal with how a human is acting. In this sense, AI is divided into four categories where you behave like a human, where you reason like a human. Then you have the other side where you behave rationally and reason rationally. By this I mean, if I ask a question, what is the 23rd square root of a huge number? If I give the particular answer, it is a rational way of approaching artificial intelligence. Instead, if I see such a question and I have certain procedures stored in the program to identify that this is not possible to be solved by a human, then the artificial intelligence program behaves like a human instead of behaving rationally. So the entire aspect of Turing test is to identify if a system is behaving like a human. So with that small background of artificial intelligence, we come into the complexity of language. When you try and communicate with your friend, for example, you want to know what are the directions to a certain place. In your head, it's extremely clear that this particular place is where the destination is. But often you would have realized how confused the other person is if the other person is not familiar with the territory or is new to town. So even among humans, when we communicate, it is quite difficult to transfer what you know into a concept that the other person can understand. Due to these inherent complexities, natural language processing by itself is quite a hard task. In fact, one of the early researchers named it as AI complete task. In the sense, NLP programs are AI complete, much like how in theory we have the NP complete problems that are quite hard to solve. So now we come to the term what we mean exactly by natural language. So languages, you can have machine language or natural language. And in the machine language, you have, say, binary, assembly, programming. That is languages that are easy for the machine to compute. Whereas natural languages are, as the name suggests, natural for humans to understand. These are like English, Tamil, Telugu, and so on and so forth. So not only do we have the complexities of natural language, we also have a wide variety of them. So at the end of the day, natural language processing is just the intersection between computer science and linguistics. And with the advent of AI and machine learning and more powerful machines, we are able to see tremendous progress in the field of NLP. Broadly, in this place, I would like to touch upon what are the various challenges of natural language processing. I have been talking again and again that it is a tough task, it is a tough task. Here I like to give concrete examples why it is a tough task. First and foremost, it is the context which makes it difficult. A very common example given in all NLP textbooks is that how do you differentiate between Bank of America and Bank of the Amazon River? So if we look at only the word bank, the meaning is very hard to figure out. The second thing is common sense reasoning. Now, language is only a tool to communicate the world knowledge. But how do we encode world knowledge? How do we encode things that even children take for granted? For example, if I say something like, I hit the ball with the bat and it went flying, I know that it went flying refers to the ball and not the bat. So these kind of things happen with a lot of experience and knowledge about the domain, about the world, and it's quite hard to implement this kind of knowledge for a computer to process. Next, we have disambiguation. I already told about word disambiguation, but we also have many other forms of disambiguation. For example, synonymy when two words mean the same, or antonymy when two words are opposite, and so on. We have so many peculiar characteristics of language that have to be accounted for. Next, we have co-reference resolution, which basically refers to what entity a particular sentence is referring to. For example, if I say Ram has 5 apples, he ate one, then the fact that he refers to Ram is a co-reference resolution. It is referring to the word Ram. Finally, we come to syntax versus semantics. It is very interesting to note that the syntax of words do not lend to its semantics. For example, if I have the word ball, then the constituents letter B, A, L, L do not contribute to its meaning. It is only together it has some meaning. So when we build mathematical models, we need to be aware of how we combine letters to form words and how we bridge this gap between syntax and semantics. However, yes, in many Indian languages, the syntax and semantics is a part and parcel of each other because there are a lot of suffixes and so on. So we can see that there are different issues for different languages, and how to handle them is the interesting part of natural language processing. So natural language in artificial intelligence has two broad aspects: understanding and generation. By natural language understanding, it means that the machine is presented with text in natural language and few tasks have to be undertaken on processing that language. Then we have generation, where the system has to generate a natural language text in response to certain inputs. So we'll come to certain actual real life examples which will make you understand why this field is so diverse and why research in this complements many applications. So we'll start with natural language understanding. The first classic example are digital personal assistants, where of course mostly the input is in speech, but once the speech part is characterized, we have to comprehend the language that's being spoken and take actions accordingly. Then we have autocomplete. Today on Google and any other form, autocomplete is a common feature when we text, when we do anything related to language in computers. Autocomplete and spell checkers are quite pervasive. Another interesting example is machine translation, where we translate from one language to another. And I'm sure when you go to different places, many of you would have used Google Translate and seen its effects, or even on social media posts seen how the translation happens. Next, we have sentiment analysis, where we want to look at a piece of text and understand what is the sentiment. For example, in movie reviews, I want to quickly and automatically judge after a movie is released whether the tweets are positive or negative. And it is quite an industry specific and interesting task. Finally, we have the very complex task of question answering, where you have both understanding and generation. We need to understand the question and generate a reasonable answer. And that has led to the very good field of chatbots, which is being used in the industry a lot, because it automates a lot of the mundane tasks that humans were before forced to do in terms of small questions that can be answered easily. Next, we have automatic summarization, where given a piece of text, I read through it and then generate a summary. All of this seems a bit difficult and removed from the problem. But once we go through this presentation, I hope you have some intuitions as to how this happens. Finally, I'd like to talk about weather report generation, which is one of the most classical examples of generation, because you have a lot of weather inputs, say humidity, temperature, rainfall, and so on, and you generate the report for that. So when we generate a report, it has to have it has to sound convincing, and it has to have less interpretations. It is not like I will convert every sensor input into text I'll say that, okay, it may rain today. That should only be the text that is generated and not what is the exact sensor value. So this makes the task difficult. And as you can guess, natural language understanding is much harder than generation. Nevertheless, generation is also a hard task to make it sound convincing and not like whether a robot is generating the text. Now we'll go in step by step into some of the intuitions. This is on the role of representation. Now the entire task and efficiency of natural language understanding and processing algorithms is on how it represents the language. Now, for example, in numerals, if we represent it in the Indo-Arabic style as 2020, and if we represent it in the Roman style 2020, we can see that mathematical operations are very successful when we do it in this style. And that is the reason the Roman style went out of use. So the Roman style had this difficulty that when we do addition, subtraction and so on, quite difficult to do the operations. Whereas the use of the decimal value system helped us represent large numbers and do operations very efficiently. So the entire gamut of research in NLP is on developing the most efficient representation of text for that particular problem. So we have three major paradigms. The earliest one is the symbolic AI. Then we have statistical machine learning. And now the state of the art is the deep learning paradigm. So I'll start with the symbolic AI. I'll dwell very briefly on it. So in the symbolic AI, it is called so because it manipulates symbols. So in the sense, for language, there are a set of rules, a set of grammars, which says, say a sentence consists of a noun phrase and a verb phrase. So these kind of rules help you understand that you can both generate the text and understand the text. So given a sentence, I can break it down into the noun phrase and the word phrase. Given a noun phrase and a verb phrase, I can generate a sentence. So this was a very convenient form of representation. And one of the earliest examples is this legacy chatbot called Eliza, where it does very simple manipulations and it basically just rephrases what you are talking about. In fact, though it was extremely simple, many humans felt that it is a dedicated psychiatric operator, and in fact the secretary of the scientist who developed this said that it changed her life, and she could not believe that it was a program and there is no other person sitting on the other side. This is because since the program just manipulates what you have told, the human mind imagines that you are being listened to and psychologically gives you some relief. So this was one of the early interesting applications of natural language processing. And then you can see the reason why it stopped being popular was that a human being cannot come up with all rules for a language. You cannot come up with what exactly to focus on. How do you manipulate the text? Because there are infinite possibilities and infinite rules to create sentences. So because of this drawback, a lot of machine learning approaches started dominating the field. With more and more data available, it became interesting to use that data to develop these rules. So by machine learning, what we mean is that, of course, you've all had some introduction, but I'd like to quickly just give this high level overview, where in a traditional program, you have some data and you have a program and you generate the output. By this, I mean, say you want to find the square of a number. Then you input 2, give the program, and you will get 4. But in machine learning, you have data such as 1, 1, 2, 4, 3, 9. So this is your set of input 1, 2, 3, set of output 1, 4, 9. And you finally have the program which says probably this is the square of each other. So finding out this program or this pattern is what we call pattern recognition or machine learning. So mathematically, this is what is represented in that, where we have a lot of points and we try to fit in what to do. Now this seems quite straightforward and it feels like we have solved all the problems that are there. But the tricky thing is we don't know the shape of the underlying function and it's quite hard to understand what to fit in, and it is only with practice and with applying data sets and algorithms we get an intuition on what would give good results. So with this background, let's see how statistical machine learning was happening for text. First is we convert the text to a vectorial form because machine learning is a completely mathematical aspect and everything has to be in the vectorial space. Now how we convert the text to a vector depends on the domain and it depends on the human developing. Then what will happen is we have a set of numerical outputs again for the input. So everything is a number. Your text is a number and your output is a number. This is not the case in symbolic AI where you directly deal with the words and you have rules for the same. So let me give an example to make this a bit clearer. So say we are working on sentiment analysis and we have a piece of text. Say something like, this was a good movie. Now this will be converted to a vector. Now I may have features such as, if the word good, nice, pretty are there in the sentence, then let the value be 1 or let it be 0. So like that I will have many features and this is called feature engineering where we develop such a vector. Now my output is also a set of numerical vectors, good or bad, and then we have a lot of standard algorithms that can be used to build the model, which will basically take, as I said before, the input and the output and develop a model that at test time can see an unknown data and predict whether it is good or bad. So with that, I'd like to give this example where we have a symbolic AI and a connectionist AI. Connectionist basically refers to the neural network paradigm upon which we'll touch briefly, but it generally means that in the symbolic idea, I encode a lot of information about the knowledge of how an apple should be. In the connectionist approach, however, I have a lot of data points and a lot of probabilities, and finally on firing some of these, I'll be able to decide whether it is an apple or not. So with deep learning, what happens is that this task of feature extraction is not there. So here, given this input of a car and I have to identify whether it is a car or not, I would develop features such as, okay, do boundary detection and find the number of circles. If the number of circles is 2, then that could be one of the features, and so on. In deep learning, however, what I do is that I allow the network to identify what is the feature, and instead I will just be giving the RGB values of the input. So after this, I will be telling that at each pixel what is the color, and I will allow the model to learn. Now you may think that this has come out very recently, but the earliest research in deep learning actually came out all the way back in 1946, and it is actually the amount of data and the machines that are available now that has led to the improvement and success of deep learning today. So before we move on to the next part of the presentation, I'd like to briefly touch upon how we learned languages. Now this is the Tower of Babel, which is a story in the Bible that says how human beings develop languages, where all humans were put in this particular tower and they were talking in different languages and they were not able to communicate. And this is a Vedic goddess who is supposed to have bestowed the gift of language onto people. Now the reason I shared this is because humans are fascinated as to how we develop this ability, and the ideas of symbolic and data driven are quite different, and it's at this point it's nice to think what is the so-called correct way of approaching language. Now the answer is that there is no fixed way of telling this is the particular way or that you have to do natural language processing. Some points that are for data driven approaches is that we don't learn complex grammars or rules when we see language and learn it. As a child, we hear a lot of language and we are exposed to a lot of data and we learn the language. Hence, it seems intuitive that we need to go for data-driven methods. But we also saw that that approach does not involve a lot of world knowledge, and the symbolic information makes it very interpretable. We can generate explanations about the language and so on. So now what researchers are moving towards is how we integrate the two approaches and still make it generalizable and usable for applications. So a quick recap of what we have discussed so far, which is how in language we discuss in the symbolic AI or in the pure classical AI approach. We use our knowledge of the language and develop rules and so on, and then we do some processing. In the machine learning approach, we develop certain features around that will be filled in by the data, and then we perform some processing. And in the deep learning approach, we do not even spend time processing the features, and we allow the machine to learn the features. Now, what this means is the symbolic AI is actually the most accurate one because directly the human intervention is there. However, it also does not generalize well because we cannot come up with all the rules for a language. So from here to here, the accuracy decreases, but the generalizability increases. And the reason deep learning approaches are so popular is that for many tasks, we don't need 100% accuracy, and a certain level of accuracy will do. And that is the strength of deep learning. So now I'll be talking a bit about neural networks and so on to give a sort of base before we go on to the language part. If anybody would like to ask some questions now, it will be fine. I'll just take like a 2-minute break and then we'll start with the slightly more technical aspects of this. So let's continue. I'll be talking about the intuitions now of the state-of-the-art methods, for which I will. Can I continue?
Yeah, you can.
Okay.
Please.
So, thank you. So, for that, I'd like to give a small recap of what you might have seen in the previous lecture on artificial neural networks. And then we'll proceed to how we apply it in text. So again, I'll be talking about perceptron, multilayer perceptron, and the deep networks. So very briefly, we'll be touching upon them. So in the perceptron, what we have is a set of numerical inputs and a numerical output. And the idea is that the output will be decided by a combination of these inputs. So it's going to be something like W1x1 plus W2x2 plus W3x3 and so on plus B. And then we have a thresholding function which decides whether these inputs, how these inputs are going to be forwarded to create the final output. Now when we see this, we can understand that the form of the equation is linear because it is similar to y equal to mx plus b, except it's in a higher dimension where we say w1x1 plus w2x2 and so on. So the way it's going to be,
Your video was off.
Okay, now it's okay. Yeah, so I was talking about the perceptron, and now I'm talking about the linear separability part, where we have a bunch of inputs and the weighted sum, such as w1x1 plus w2x2, form the equation of a line. So this means that if my outputs are of the form such that they are all of one type on one side of a line and the other is on the other side, which means that if it is something like this, where these 3 points belong to one class and this point belongs to another class, it is possible to find a line such that it can be separated. Similarly, here also we have such a line. But in the case of XOR, where we have alternative outputs, it's quite hard to generate a line which will take care of this. So this is the drawback of a perceptron, and to overcome this, the multi-layer perceptron was developed. Now the multi-layer perceptron, what it does is that instead of directly going from the input to an output layer, we have one more layer here which gives us more flexibility. So for example, if we have 4 inputs and if we have say 2 power 4 hidden layers, then every possible combination of it is taken care of. And hence this problem of linear separability is not there. Mathematically, what this means is that complex functions are modeled in this space, and multi-layer perceptron has been around for quite some time. But adding more and more hidden layers and more complexities has led to the evolution of deep learning. So the reason is that neural networks have this nice feature, which is proven by the universal approximation theorem, that says that given set of data, it is possible to come up with a generalizing function. But the problem is, for that we need to find an accurate set of weights, or in the sense an accurate set of coefficients for the same. So for that, these are called feed-forward neural networks, where the computation is in the forward direction, but we train the weights in the backward direction. By training the weights in the backward direction, what it means is, by this what we mean is that, by training in the backward direction, what we mean is, first we have some random set of weights and we generate the output. Then we see what is the difference between our current output and the actual expected output, and the difference is propagated backwards, and then we train the model. By train the model, we mean the different weights we are computing. So because we do it in this manner, the training method is called backpropagation. Now what is the difference, as I was saying, between multi-layer perceptron and deep learning? It's just that we have much more hidden layers and many more nodes in each hidden layer, and what that means is that we can compute highly complex functions that model the real world data well. In fact, some of the leading scientists in deep learning say that perception tasks that require less than a second for human beings are the ones where deep learning is most successful. So for text, there are a few neural architectures, as you might have seen the LSTM architectures, and then the sequence to sequence model. So let's have a quick overview of that. So what we mean by sequence to sequence? It very simply put is just an input sequence that's being converted to an output sequence. So our input sequence can be anything. So in this case, actually I shouldn't have put image. Let's take a video and you have a caption. So video is a sequence of images and the caption is a sequence of words. Similarly, for question answering, your text is a sequence of words and then you have a sequence of words as the answer. So a sequence to sequence architecture is quite a versatile one, where a large number of applications can be built using the same architecture. Also, you can have machine translation, where you convert from one language to another, which is yet another application of sequence to sequence. So while discussing sequence to sequence, we need to first see what we mean by sequence. Sequence is nothing, from a layman perspective, a collection of objects where the ordering is important. So in the dictionary definition, we have a set of related events, movements, or items that follow each other in a particular order. So in both of these definitions, we see that the word order is quite important. So when we think about what are the properties of sequences, the first thing is that the ordering is maintained, and it is important which follows the other in a sequence. The second interesting thing is sequences have variable length. Now throughout the discussion, we have only been considering inputs where the input length is fixed. Sequences, however, are not like that. Like a word such as cat is just a sequence of 3 letters, but a word such as presentation has a long sequence of letters. But both of them are words in English, and hence both of them have certain characteristic features that lead to language understanding and processing. So for that, we'll start with the intuition. So throughout, we're going to be seeing the intuitions and not the math behind it. So the intuitions of a recurrent neural network is to capture these two aspects of a sequence. Now this might look like an unfamiliar diagram, but it's just the previous multi-layer perceptron we saw that has been shifted into a horizontal format. So what this means is I have an input sequence and I'm generating the output sequence. And this, in the sense of a word, can just be say if this is C, this is A, this is A, this is T, and this is T, and full stop. So it's basically capturing a word using the sequence of letters. And what this means is a lot of the weights in this are fixed. Now, in a normal neural network, the weights vary quite a bit. Each connection has a different weight. But in a recurrent neural network, we have many weights that are exactly the same, which allows this kind of a diagram. We'll be seeing what this means. So the first is that the connections between the hidden layers have a common unifying weight, which in this case means V. What this does is that it ensures that sequences of varying lengths also encode some information that is characteristic to that particular language. The next thing is that input is given in a time-spaced manner where information from the previous hidden state is passed to the next hidden state. So in a normal neural network, you would not have this connection. Directly it will go from here to here, and now we have an extra connection that basically suggests that between hidden layers there is a transfer of information. Now this is the one that encodes order information. So by choosing this weight V that is tied across all of this, it elegantly captures both the arbitrary length sequence and the order information. Now training this is a bit hard because once I have a set of inputs and outputs and I am back propagating the weights, many of them have this constraint that they have to be equal, and hence the flexibility is reduced. Because of this, RNNs suffer from a problem that is known as the exploding and vanishing gradients, which means that if one of them becomes 0 or infinity, all the weights across the network would do so. To overcome this, long short-term memory networks were developed, which basically has more room and more flexibility because it has these three gates known as input gate, output gate, and forget gate, which controls the extent of incoming value or outgoing value, or even suppresses some amount of information, which makes sure that this problem of exploding and vanishing gradients do not occur. And LSTMs and the bidirectional variation of it, so which means that there is another connection in the reverse direction, have begun to dominate the field for representing language. So in sequence to sequence, how we employ RNNs or LSTMs is that we have the input sequence and an output sequence. So this sequence is for a word and this sequence is for an entire sentence. So it's basically say a sentence to sentence transformation. And what we do here is that we have the input sentence, we train it and pass some information as the bias to the output sentence. Now, while training this is fine, though the diagram doesn't say, the decoder will also have a set of inputs and the encoder will also have a set of outputs, that is ignored. Now, during training that's easy because we have the pairs of encoder and decoder, but during inference that is not possible because we will have access only to the encoding sentence. So for this, a method known as teacher forcing is followed, where first what we do is we give a particular sentence and then we enter full stop or an end token here. With that, it will generate what is the first word. Now, given the first word, That will be passed here, and then we will get the second word. Then we will have the input sentence and the first and the second word here, and we'll be able to get the third word. So in this way, we solve the problem of not having the decoding sentence during the training process. So this is the overview of sequence to sequence architectures. So now we come to how we employ all these deep learning architectures for natural language processing. For that, we will spend some time on word representation and how word representation is the one that has made deep learning very successful for language understanding. So by word representation, I mean how do we represent words as vectors? So traditionally, before deep learning became popular, word vectors were done using this terminology called as one hot. What this means is, say that I have only one sentence in my corpus, which is dog likes a cat. So I will have a vector of length vocabulary, and I will just have certain flags to say which word refers to which part of the sentence. So if I say dog likes a cat, then dog is position 1, likes is position 2, is position 3, and cat is position 4. So this is the way I will represent all the words. Now this has some problems. One is it is a very high dimensional vector in the sense, if I have a vocabulary of size 30,000, then all my vectors are of size 30,000. And people who are familiar with machine learning will know that we have the curse of dimensionality as we move higher and higher into space. Now, this means that our processing abilities decrease because the dimensions are very large. Not only do we have high dimensional vectors, we have sparse vectors. In this entire vector of length 30,000, only one of it is going to be 1 and the remaining is 0. And this also brings us to the fact that syntax and semantics are quite different in the sense the word duck is equidistant from both the word bird and school because we have it. In fact, all the words form a basis of the vector space, and it is quite difficult to say that, like, actually in a application point of view, what we would like is that the word duck and bird are quite close to each other. Now there are a few advantages, a few evolutions of this one hot vectors that were developed, such as singular variable decomposition and so on, which solve the problem of sparse vectors, but still it did not lead to better results. So what this means is that word representation in this form became unpopular, and for machine learning tasks, what became the norm was to basically use indicator words such as good or bad or things like that, or features from WordNet, which is a dictionary basically that tells you how inheritance happens and so on. It has a lot of word knowledge which could be used to develop the features for machine learning. Now instead what we wanted to do is develop a vector space model where we have all the desired features for the words in the vector space. So for that, we came up with this idea that a word is known by the company it keeps. So what this means is, in a deep neural network with the input layer, hidden layer and output layer, as a side effect of another task, word representations were learned. For example, as input, I'm going to give only one hot vectors, but this particular hidden layer actually allows me to build a compact representation with many desired tasks. So my input layer is going to have one hot vectors, my output layer is also going to have one hot vectors, but the hidden layer has a compact, dense representation that helps us build good word representations. Now, because this is embedded in the model, commonly these representations are also called word embeddings. So what happens is that, first of all, we have a fixed length of the vector. It is not dependent on the vocabulary size. Next is we have a semantic representation because it was found that the word king is closer to queen than novel. And also, interestingly, the distance between king and queen is similar to the distance between man and woman. Next is we have fractional values in the vectors, so they are not sparse. And the greatest advantage from an industrial perspective is that every time we don't have to do this learning. Once I learn for a word what is its corresponding representation, I can use it as a lookup later on. And this is what helps as a seed for all the deep learning algorithms for the particular tasks that are there today. So as I was saying, some of the examples is that the distance between man and woman is similar to the distance between uncle and aunt, and again it is similar to the distance between king and queen. Now, apart from that, the distance between king and kings is similar to the distance between queen and queens. So we have the gender relationship that is qualified here. We have the singular plural relationship that's qualified here. So as more and more of these vectors were visualized, more and more advantages were gained from these inferences. Now, we also have things like the distance between slow and slower, and the relative distance between slower and slowest is similar to the distance between short and shorter and shorter and shortest. So these images are obtained using dimensionality reduction, where we can view large vectors in 2D space. Usually some of the classic examples are PCA and so on. Or now the popular TSNE is used for finding out the low dimensional representation of vectors. And this gives us a lot of information about how good these particular representations are. This is another interesting example. When we look at vectors that are around the word apple, we find the word mango, which is a type of fruit, as apple. We also find words such as Microsoft and IBM, which says that it is also disambiguating between many different meanings of a particular word. And that makes this once again very interesting and has a wide variety of applications. And now the famous GPT-3 model has been developed over a large data set, which is giving more and more complex inferences in the same way. So to recap, what does this mean? So first is that the word vectors are useful for all the problems in NLP, not just the development of the word vector. So it's used in all the things I was talking about from the beginning, say sentiment analysis or machine translation or question answering and so on. And the reason this has happened is what we were discussing when we saw deep learning. And one of the biggest advantages is that it is unsupervised. There is no labeling here, no human intervention. Hence, you can feed in larger and larger texts and develop these word vectors. So one of the popular ones is Word2Vec, developed by Google, where we can see that neighbors are car and bike, book and magazine, queen and king, and so on. So to give an idea of how this works, let's have a look at the training data. So here we have this concept called context window. So I was saying that as a side effect of another task, this was developed. One of the tasks is that given a set of say 4 words, I want to predict what the next word is. So these 4 words form the context for that word. Now in this, we are taking a context window of length just 1. So I have things such as eat an apple, eat is followed by orange, eat is followed by rice, drink is followed by juice, and so on. Now what the model infers is that the word eat co-occurs with the words apple, orange, and rice. Similarly, the word drink co-occurs with the words juice, milk, and water. So on and so forth. Then we also have things such as orange juice and apple juice and so on. So what this leads us to develop is that co-occurrences help in disambiguation, help in deciding the neighbors, and so on. So this is again reiterated by the first concept, where we said that a word is known by the company it keeps. Apart from predicting a word given the context, the reverse task of predicting the context given word is also used to develop these vectors. So now we get concepts such as milk and juice are drinks, because that co-occurs with the word drink. Then we have concepts like apple, oranges, and rice can be eaten. And apple and oranges are also juices, and rice milk is a type of milk. So this is how the powerful nature of the word vectors is developed. So to show it in the neural network perspective, we have concepts such as apple. So the vocabulary is repeated on both sides, but the way it proceeds is how they are connected. So drink and juice are connected, hence some weights are propagated. Drink and milk is connected, and so on. Next, we have the popular glove vectors from the Stanford University, where they go one step further in its development, where what they say is that instead of predicting what word follows the other, I will predict an entire probability distribution over the words and see which is possible. So the word that ice will be followed by solid, gas, water, or fashion is given by these weights. Similarly, probability of steam, and so on. Now, probability that ice or steam, what is the overlap, is given by this. So we have co-occurrence probabilities, which makes it a slightly stronger model. Having said that, however, it is not that once we use glove model for developing the vectors, the old word-to-vec vectors are useless. For every application, we need different kinds of knowledge that is captured by many of these models. But the problem is that which is a problem in all deep learning things, is that these are inferences we are making, but we don't exactly know what concepts are being captured. And it is also difficult to again replicate the results. And it can, of course, take a long time to train, and it can also have a lot of energy efficiency issues. But the advantages are that it's highly generalizable. You can develop a lot of applications, and once trained, you can just look it up. What this means, however, is that the word embeddings that are developed, however, will be based on the data on which it was trained. So if you have a very specific domain, say the domain of physics, then the words are completely different and you need to train it again. So even though we have the advantage of using pre-trained vectors, depending on domain to domain, we might have to train them all over again. And for that, we need more resources and more time, as we see in all deep learning applications. Now, before sequence-to-sequence models were developed, what was the initial strategy was just that given a sentence, I will concatenate the word vectors. However, this has a problem that it will be varying and it is difficult to generalize. The other idea is to average the word vectors and create a single vector. But what all this means is that many different factors are collapsed into the average vector, and that might not lead us to having good results. So if I say something like the movie was not bad and the action scenes were good, and you average good and bad together, you might get something like a neutral sentiment, but actually the rest of it might be going to a good sentiment. So averaging and concatenation were not seen to be very effective, but they were a good first step for very simple problems. So that is when we had the discussion of sequence to sequence already. And now we can appreciate that here instead of giving letters, we can directly give the word vectors and represent a sentence. So that is how the word vectors now feed into the sequence to sequence model. And we can understand how important the development of these word vectors are. Next, we come to this concept of attention. When sequence-to-sequence models were applied on industrial problems, it was seen that many times the result is not as efficient as would be required, simply because there's not enough data, or that a particular, say for machine translation between Indian languages is quite hard because data is quite less and the rules of data are quite complex. So that is when scientists realized that we could have something like attention, where it means what part of the input I need to pay attention to. So if I say, how are you? And this is some Japanese text that is the translation of that, it might read that the word how alone is important to generate this text. So I want to say that, look, pay attention only to the first word, say, compared to the other two. And that is what gives us information in the translation part. But what this means is that once again, the user has to come up with where to pay attention. To overcome this, what people have done is that apart from the neural network weights, a set of attention weights have been applied on top of the encoder part, which is passed as bias to the decoder. So that way you don't have to manually encode which is important. And just like how we saw eat rice and drink juice and so on, the network itself will learn how to what weights develop the concept of attention. Next, we come to the concept of transformers, where transformers are a set of complex attention mechanisms where they also convert an input sequence to an output sequence. And the idea is that instead of having a long sequence of LSTMs on the encoder side and the decoder side, what we do is that we just send the set of words and we apply attention in a complex way on top of each other. And this is again sent to the output. So there is a set of attention in the input and a set of attention in the output, and that helps us generate the sequences. Now what happens is that here, because there is no sequence or LSTM going from one place to another, we have to encode which words refer to which part of the equation of the input. What this means is that if I have a sentence, a boy is sitting on the grass, then in the sequence to sequence part, there is no problem. I will just pass it in that order and there is a connection between the words. However, in a transformer architecture, what I need to do is something called positional encoding, where I need to say that the is in position 1, boy is in position 2, and so on. And this informs the transformer about the sequence capabilities and finally gets the output. Now this architecture was introduced in 2014-15, I think, using the title "Attention is all you need." And it was shown that attention is having a lot of advantages which something as difficult to train as LSTMs is not having. Now, once again, just like sequence to sequence models, this also has a problem of teacher forcing, because you do not at the time of training have both the access to input and output, and you generate one by one as mentioned before during sequence to sequence. So with an introduction to transformer, we come to the next architecture for text known as BERT, which is one of the most recent applications of the transformer. So what it does is that it uses the transformer to generate context-dependent representations of the vector. Now here, instead of how the other word vector models happen, what we do is that we don't just generate what is the vectorial representation for a particular task. Instead, what we do is that we say that we have a trained model. So the trained model will take your sentence and generate the vectorial representations for the words. So instead of having a lookup in the way of having, say, given a word, this is the vector, We now have a trained model itself where we will pass the sentence and get the vectorial embeddings. Finally, yes, we will use the embeddings however we want for classification or so on. So this has been shown to generate much better embeddings in terms of context disambiguation. However, a word of caution is that it's quite hard to use this because you are looking up an entire model and not just a simple lookup table. And hence, if your domain is naturally quite context free, it does not make sense to invest in this. And there are many offshoots of this like Robert, Albert, and so on, which have proposed more and more, more and more improvements on this. And they develop superior quality embeddings for text. Now, I'd like to give a bunch of resources if you're looking at it from the engineering perspective, which means that given text, I want to have a hands-on feeling on how we can process the text and generate some outputs. So you can use a part of speech tagger to get the noun, verb, etc. of the sentence and use it in a bunch of rules. So for example, I want to identify the names in a sentence. I can use this to generate that. Next, we have a dependency parser, which is more complex. So a part of speech tagger is also known as a constituency parser, where we generate what are the different words and so on. In a dependency parser, we generate much more complex relationships, such as subject, object, and so on. So what this does is that you can, so these tools are already developed on large data sets. So that helps us to quickly use in our applications what has already been trained. We have spent quite some time discussing embeddings, and we saw word to vector and glove, and you can add BERT and so on, and even GPT, which has become quite popular. And there are some basic steps for all of this that we need to implement, such as the tokenizer, which basically splits the sentence into constituent words. Now, in our normal usage to split a sentence into words, we would just generally split the sentence in using the space and get what are the words in between. However, it's quite interesting to note that there is a separate field known as sentence boundary detection, which develops superior tokenizers. Why there is a separate field is that language does not follow very strict rules, except something like Sanskrit maybe. So, for example, in English, you have something like a full stop to indicate the end of the sentence. However, we also know that the same punctuation is used to say 3.4 or 4.7 and so on. Hence, even something as simple as tokenizing becomes quite hard, and we already have a lot of open source implementations of tokenizers that help us in this task of splitting the sentence into words. That is what allows us to load embeddings later on. Then we have something called the named entity recognizer, which recognizes whether a certain word is a particular category, such as person or a place or a organization and so on. So for this, we have a lot of resources such as Stacy, Stanford NLP Toolkit, NLTK, Jensen, and so on. And these are two blogging places where you can brush up on the concepts or code snippets to identify these. Now, a word of caution to all of this is that all of these tools are developed on texts that are available primarily for the English domain, and not only English domain, for a particular class of say US, UK English. So for example, I worked in understanding word problems, math word problems, which I'll be talking on as a case study in the end. And word problems in India with nouns such as Ram and Shyam were not recognized by these named entity recognizers. That is one interesting aspect of research. And the second thing is that we have things such as person, place, so on. So the word, for example, the word Sita in my code was recognized as an organization. And that's quite an interesting thing. Then the reason deep learning and embeddings is so popular is that except for this load embeddings part, the part of speech tagger, dependency parser, in-ear, all of them used very, very different machine learning algorithms that are tailored for this task. But what deep learning does is using this common aspect of word embeddings, we are able to develop robust methods of generating these embeddings for these tasks. Now, from the research angle, we have a very useful site known as nlpprogress.com, which for every research problem has the latest papers, the latest values that are state of the art, and the abstract of the paper that has achieved this. And this helps you get started on some small tasks and gives you an idea of how to proceed. And if you need to develop your own deep learning algorithms, you can use TensorFlow, Keras, PyTorch, and various other fields. And one of the reasons research in NLP happens very fast is that all of these are open source. You can contribute to them, you can use them, and develop better and better algorithms. And there is a vibrant community that you can ask questions and generate applications. Now, to get started into researching in natural language processing, one thing is for the coding part, you need to know Python to a large extent. Then we have a seminal textbook on classical NLP by Juravsky, which touches on various concepts and gives the differences between all the three paradigms. Then we need to learn the math. So in this, I'm not touched much upon the math because my idea is to introduce the broad intuitions so that when you read a particular text in NLP, you have some idea what it refers to. But to get into research, what you would require is the math behind machine learning and deep learning for NLP. Of course, a word of caution is that we only have a high level understanding of the math behind deep learning, and the theory of deep learning is a fast evolving architecture, an area which is what is going to help us develop better algorithms in future. However, we need to have a rudimentary understanding so that we can press towards and go forward in the field. So now I'd like to talk briefly about my research during my PhD, which is what drove me and gave me actually a very clear insight on how the various methods differ. So I worked on representing word problems in text. So like I said, the entire discussion what we are having was basically how to convert text to an efficient representation, whether it was word vectors or whether it was in sequence or transformers. So now in this particular word problem, John has 5 apples, he gave 2 to Mary. How many does he have now? Even in this extremely simple word problem, which even an elementary school student can solve, the problem is that the machine has to understand he refers to the word John, needs to understand that the number 2 refers to apples, and on the mathematical side, it means that Mary gained 2 apples, so there's an addition aspect, and John lost 2 apples, so there's a subtraction aspect. There's also a temporal ordering which says that initially John has 5, then he gave 2, how many does he have now? So in fact, question answering is one of the toughest challenges in deep learning as of now, because we need these answers to be interpretable and accessible for people. So first we dealt with knowledge-based approaches, which is the symbolic AI approach, where we used cues from psychological literature to identify what are the various types of word problems available at the elementary level. And this was filtered with a bunch of rules. Now these rules were developed on parsers that were developed using data. So there's a sort of flavor of both in this. And the idea is that it's very interpretable because you have come up with the rules and you can understand from the output what is happening, and is extremely accurate. But it also means that only very few problems are going to be identified by this task. And it involves a high rule making effort. What this means is that I once made a bunch of rules for one particular data set of around 200 word problems. And when I tested it on another data set, say of 100 problems, it did not identify even a single unknown problem. You might feel that that's quite hard with such simple problems, but language is very hard to generalize in the form of rules. But the explanations that were generated were of high quality. So by rules, I mean things like I would manually remove conjunctions, manually do not manually, use tools that are there to do co-reference resolution, and I would insert missing entities and develop a sort of intermediate representation like this. And this would encode the mathematical information. Next, we moved on to the data-driven approaches, where what we do is that we use data to guess the equation. So, like I said, how about feature extraction? We decide on features such as, say, certain words are there, like altogether and so on, or if there are many number of entities, and such features would help us develop a vectorial representation of the word problem. Now, this was far more generalizable and it was able to identify many word problems correctly. So, identifying what type of word problem was handled well, and it has moderate precision. It is not as good as the knowledge-based ones, but once again, it is not interpretable. But the advantage is that data-driven approaches are comparable. So we have a data set and we can compare it across different algorithms. So in knowledge-based approaches, the usual idea is to show a particular word problem that has been solved or to show the complexity of word problems that are being solved. But the comparison aspect is lacking there. Here, there is a high annotation effort. For example, I might have to physically write down what is the equation for every word problem. But that is definitely much easier than coming up with a bunch of rules. Finally, we worked on deep architectures where we directly use the data and the embeddings to guess the answer or the equations. Now, this is not at all interpretable, but it is highly generalizable. And as we have seen throughout this lecture, the effort is directly proportional to the quality of the data, the algorithm, and the machines available. And the sad thing is that word problems is quite a niche domain for which enough data is not available. And what we have is that, so what we did as part of our research is we generated data where we augmented the data set and created duplicates of a word problem. So if I had something like John has 5 apples, he ate one, we'll generate another data set such as Mary has 5 apples and she ate one. So these kind of duplicates were generated to create a large data set, and then we applied these deep architectures. So people feel that deep architectures are possible only with large data. That is not so. You can use a small data set and use deep architectures. But the problem is your inferences will not be of good quality. Now, deep architecture will typically have around thousands of parameters. And a usual rule of that thumb is to have 10 times the number of parameters in your training data. So 1000 parameters means you need to have at least 10,000 training data points. And this is just a rule of the thumb. But say you have an architecture with just say 50 data points, then you just need 500 problems, much like machine learning data sets. So it completely depends on the complexity of your model. And of course, then the question comes, do you call such an architecture deep architecture if it has such few parameters? So all of these are interesting questions. But what I'm trying to show that even today, it is not that the deep architectures have given us all the solutions and natural language processing is a solved problem. What this means is that still natural language understanding remains an AI complete problem, and we need to spend much more effort into developing this. And to motivate what are the challenges still remaining in semantic understanding, I'd like to once again delve into my area of word problems. So here we have this word problem. Sally has 3 apples, John has 4 apples, Kathy has 5 more than Sally. How many do they have altogether? So what this means is one person has 3, another person has 4, and another has 5 more than the first person. So in this one problem, you need to solve the sub-problem that Kathy has 5 more than Sally. Now what this means is that the equation is of the type 3 plus 4 plus 5 plus 3. So that means the number 3 is repeated twice. So in usual data-driven models, what people would do, or what the algorithm would analyze, is that, okay, there are 3 numbers, 3, 4 and 5. How do I use operators to combine them and get the equation? But that would fail. As you can see here, the number 3 has to be repeated. For this to work, what that would mean is we would require a lot of examples in this format to generalize that. And usually such things are quite on the outlier side, and it's quite hard to generalize these kind of concepts. Another example in this is linear equations, where you have Sally is 10 years older than Mary. In 6 years, she will be twice as old. How old are they now? Now, when I say twice as old, the equation is quite manageable. We have the numbers 10, 2 and 6 in this. Once again, we have 10 and 6, and we have to somehow encode that twice refers to 2. But assuming that with data, we are able to take that. It becomes more complex when it comes to thrice. Because once we use the word thrice, the equation is s minus 3m is 12, where the number 12 doesn't even occur in the word form. And that is because of the concept of age, where all the variables' age is being varied. And these are some of the challenges in semantic understanding. And to sum this up, what we often use is the word Chinese room experiment, where if we have this room of a dictionary, where we say that, okay, I have given you a sentence in Chinese, and a person looks it up and gives the translation, or the reverse, that is, I given in English in Chinese, or from Chinese to Chinese, whatever. But the fact is that the person doesn't know Chinese. The person looks at the input, finds out the answer and throws the answer out, and that's it. When this person comes out of the room, they have no idea of what the language Chinese is at all. So what this means is that at this point in time, deep learning is doing exactly that. It is identifying a bunch of patterns and repeating that pattern outside without gaining conceptual understanding that will lead to better applications. So to sum up what we discussed in language, we need to go towards better implementation of semantics. Yes, with embeddings, we have come a long way and revolutionized the field of language understanding. But more complex ideas of question answering, where we have temporal, positional understanding and lot of world knowledge that is to be embedded in these kind of mathematical and highly flexible architectures, that is what is going to lead research forward. The next is interpretability. We have come far away from interpretability from the symbolic era, which is why even when I was working on solving word problems, we were not able to deploy this, say, for teaching students, because it is not interpretable, and there is no guarantee even that I will get the correct answer. So the idea is that we move towards interpretability such that we are able to get better results. It is not like there is no work being done. Even in the field of word problems, there is a piece of work which generates the explanation for the answer. However, just like the Chinese room experiment, it is but a language modeling task which generates the explanation, and very domain dependent. In fact, over 1 lakh word problems, it was able to solve only 22% of it. But the 22% it solved were from a wide variety of domains, and a large number of operations were possible. Next, we come to the task of fairness and ethics. Fairness and ethics is pertinent in today's world because text and large amount of text is being used to develop these embeddings. Like I mentioned before, king and queen are close together. But unfortunately, so were doctor and nurse. So what it meant was king and queen has the same distance as doctor and nurse, which implies that the male is the doctor and the female is the nurse, and which again implies that female doctors and male nurses are quite less in number. Now, these kind of ethical issues and gender bias is what led to many big corporates to drop AI algorithms from filtering out resumes, because these algorithms are built on biased data, and removing this bias from data has become a major concern for AI researchers and an active field of research. Last, I'd like to talk about catastrophic forgetting. Now, catastrophic forgetting is an application of deep learning networks. So once I generate word embeddings, for example, say for the word cat and dog. Now, again, if I use a new training data and generate the word embeddings for table and chair, it will no longer be able to recognize what is cat and dog unless you had saved it before. Now, that is not how humans learn. Human beings understand once we see images of cats and dogs and then we see images of something else, we are able to understand the difference because we have this concept of memory and we are able to save aspects of our knowledge. So, though our brain and neural networks are finite, we are able to also have this concept of huge memory, which is not being captured by deep learning networks very well. So for this, there were architectures such as SOAR and other planning architectures that captured memory aspects well, but currently deep learning do not have these aspects. So yeah, I'd like to conclude with this. These are some of the interesting future directions, and you can connect with me for future questions, and this is my website, and yeah, I'm done with my talk and open for questions.
Yeah, questions from the audience?
Ma'am,
Yes. Hello.
hello.
Yeah. Tell me.
I'm actually planning to write a journal.
Okay.
So, could you tell me few interesting topics close to AI?
Oh, you are asked. Okay, so I had mentioned this website, right? This nlpprogress.com. There are a lot of interesting topics there and a set of papers that you can read. So you can start there and see what is interesting for you. Like how I was talking about sentiment analysis, there are a lot of tasks that you can read there.
Thank you.
Hello, good evening, madam.
Yeah.
This is Praveen Kumar, assistant professor from Vignan University, ma'am.
Hello.
Yeah, can we think that one, madam, this word representation has came to a saturation kind of thing with this word to wake and glow wake and okay, and other representations, this transformers and attentions.
By saturation, I think you mean that more research is not being done on these embeddings.
Yeah.
That is quite true in the sense because they are very elegant, they have been used for a lot of applications, yes.
Yes.
And they have been shown to do a lot of things. But when I am using it in practice, even though technologically BERT embeddings are much better than word to vec, as I was saying, depending on each application,
Yeah.
I see sometimes that even word to vec is better than the BERT embeddings. So the fact remains that though we say something is better, there is still a lot of research to be done on what exactly is the knowledge that is being captured by each of these embeddings for what domain and so on. So though there might be a saturation on how we are doing, I don't think there's a saturation in embeddings as such because there's still a lot of work to be done. In fact, a 2018 paper or something came up with a way of combining different embeddings and extracting the knowledge from them. So yeah.
Finally, people are okay. So mixing up these existing methods. Okay, so to come up till now. Okay, so
Yeah.
because the word to wake was the breakthrough, which I understood. Okay, so from that onwards only the people are going on. Okay, so towards the other things. This glow wake and okay, so this glow wake and word to wake came on same year, I think. Okay,
Yeah,
so
20.
parallelly. Yeah, ma'am.
Yeah, that's true. So, though it feels saturated, that will always happen in research. Like at some time, SVM was very popular, then it became
Yeah, yeah.
saturated. So that's how research is. So, yeah.
Okay. Thank you, ma'am. Thank you.
Yeah, any other questions? Hello?
Hello.
Yes, sir, proceed.
Uh, yeah, is SOWMYA there?
Yeah, hi.
Yes, yes.
Hello, madam. This is Mr. Ramakrishna Rath, Assistant
Hello.
Professor, PhD Department. Yeah,
Hello.
just yeah, is it audible, madam?
Yeah, it is. Please continue.
Yeah. So my question is, madam, if we consider text summarization,
Yeah.
which is an application of NLP, so how can you describe that machine learning approach or deep learning approach or some other approach is better for text summarization in future detection?
Okay, so text summarization, first there are like two types of text summarization, abstractive and extractive. Where
Exactly.
extractive, you take the sentences directly from the text, and abstractive, you generate the text that is there. So there's nothing like this is better or that is better. It's just that things have evolved over time. So initially there was like text rank and lex rank, which had like page rank kind of algorithms to generate the summaries. And now we have the deep learning approaches which model the text and generate the summary. So it's again one kind of sequence only, where you give the input sequence of the text and the output sequence of the summary, and you generate the summary. So what we see is that the deep learning approaches give more intuitive summaries, which is not possible in the old methods. In the sense, the text is quite human-like and is close to human application, as compared to the machine learning approaches. So what this shows is that because of the value of embeddings, we are getting better summaries, and when we see the rouge score or the blue score, it is doing better. And it more research has to be done to say concretely this is only better. But as of now, I think the deep learning approaches are doing better for summarization.
Okay, madam. In connection to that,
Mhm.
so I would like to ask further. So how can we measure the perfectness of an algorithm, whether it belongs to machine learning approach or belongs to deep learning approach is the better one?
Okay, so one is we usually in research terms we go by the empirical result. We use data sets and find out which is better. Now there's of course a trend of giving mathematical justifications for why that happens. For example, for my problem of word problem solving, we first went with the empirical approach to show that this method is having statistical significant results. And then we did some visualizations, just like how here we are showing that king and queen are close together. We were
Yes.
showing that word problems that were similar were close together in the vector space. And so there are many ways of showing that some algorithm is useful or that it will generalize either through visualization or through empirical. Ideally, we would want to move the area to developing mathematical proofs that this is the reason why this algorithm is working, so that even if empirically the advantage we have is very less, maybe say only 3-4 decimal points it is doing better, but if I can show that it is better from a theoretical perspective, it adds more value. So that's why this theory of deep learning is becoming more popular day by day.
Yeah, thank you, madam.
Yeah, hello. So any other questions from the audience?
Ma'am.
Yes, please. Proceed.
Hello.
Hello, ma'am.
Yes. Yes.
Yeah, proceed.
Ma'am, actually, this question is about machine learning.
Okay.
So, I have come across many algorithms such as k-means, SVM, and so on.
Mm-hmm.
So, are they still being used, or there are many advanced algorithms already?
Many things are being used. Even in fact, recently there were for some particular task, it was shown that SVM was doing better than the deep learning approach for some particular task. It depends from domain to domain and many other things. And right now, I worked on an ethical version of k-means for clustering. So yes, many of these algorithms are still in vogue, and because machine learning algorithms are of course easier to implement, they take less time, and for your particular application, it might give better results than using a deep learning approach. And from a research perspective, yes, work is still being done on the older algorithms. In fact, I met someone working um, in the intersection of rule-based and ML, because it gives an interpretability for the medical domain. For example, if I'm in uh, a research field which is trying to discover what are the factors for Alzheimer's, using a deep learning approach is very hard to do that kind of causal analysis. So, using a bunch of rules and the probabilistic version of rules, it's much easier to come up with causal analysis. And you'd be surprised to know many of the papers get accepted in medical journals to show that this is a feature that has been proven by data that was not available to doctors before. So all the various fields of ML, AI, and even symbolic AI are there in different percentages and flavors depending on the application. And the beauty of deep learning is that it's highly generalizable, irrespective of domain. That makes it quite popular for most of the approaches.
Thank you.
Yeah, any other questions from the audience, from the participants? Hello? You can give your feedback, at least otherwise. So few of you can share your feedback on the talk. So if you have any doubts, you can, but otherwise you can share your feedback.
Madam, it's very nice to hear from you, ma'am. From the starting or inception of the NLP on
Hello, Praveen sir, your connection, your audio is lost.
yeah, ma'am. Okay, so just now power has gone and came back.
Yeah, okay.
Yeah. Soumya ma'am, it's very nice to hear from you. Okay, so from the starting of this natural language and from the inception to, okay, so different ways and understanding and generation, and from there to moving towards symboling to machine learning, and from there to deep learning. So we are very happy to hear from you, ma'am, from the starting point to up to the latest technology. We are enough fortunate to listen your lecture, ma'am. Thank you very much.
Thank you so much.
Yeah, anyone else would like to ask questions? Hello? Hello? Sharif, would you like to ask? You are unmuted.
Hello.
Yes, yes.
Yeah. I'm have a question regarding transformers actually.
Okay.
So let us say I'm working on a called neural machine translation. I want to translate a Telugu sentence into Hindi sentence.
Okay.
So coming to the dataset, I have a very small dataset.
Correct.
So for that, what I want to do is I on some other task. So how can I use this for from a particular task, ma'am?
Sorry, I'm not able to hear you.
Your voice was not clear. Can you repeat?
Yeah. Hello, ma'am. Am I audible now?
Yes, yes. Now it's fine. Better.
Since the size of dataset is very small, I just want to use a pre-trained transformer. So
Okay.
can you tell me how can I use that for my task?
Okay. So if you already have, so this it comes in like transfer learning where you already have a trained transformer, and you can look up machine learning translation frameworks that have already been trained and use it. So you use the model and you train it again. But the problem with that is probably the trained model would have been on European languages. It is quite hard to generalize for Indian languages. So I have also worked on Tamil language, and the problem with South Indian languages is that the words are very long sometimes, and there are a lot of suffixes, and there's a lot of meaning in those suffixes. So how do you split a word? Do you split it at a word level, or do you split the suffixes? And there are a lot of issues there. So the general idea with machine translation for Indian languages is to not go for transformers and use machine learning approaches that use less data. So the first thing is you have to develop the embeddings for particular language. So there are already works for Telugu which have Telugu embeddings, and they have to be so embeddings. It's very easy to get a large data set because you just have to take say Telugu Wikipedia or some Telugu texts and train it and get your embeddings. And I think there's already a data set for that. And once you have this data set, first you can try say sequence to sequence or something with less parameters. Similarly, transformer also there are few parameters that you can control, that you can reduce and use it. But I suggest you go for machine learning techniques first with less data and see how it works, and then go for the transformer related ones. And there is this website on GitHub known as Indic NLP, INDIC, which has a lot of resources for Indian languages, whether it is corpus or embeddings and so on. So you can have a look at that to start off working on machine translation.
Okay, thank you, ma'am. One more question actually.
Yeah.
So coming to the embedding, whether character level embeddings are better or word level embeddings for machine translation?
So in machine translation, we usually use character level embeddings only. Word level embeddings usually introduce unnecessary complexity. And usually use character level, but there is also value in word level. It really depends on the domain. So for example, for translation, I think character level is better.
Okay, thank you, ma'am.
Thank you.
Yeah, any other questions from the participants? You can share your feedback on the session. I assume that there are no more questions from the participants. Okay, let me give the closing remarks. So thank you, SOWMYA. Thank you for the detailed lecture on natural language processing and its applications. So you have introduced various NLP applications and various machine learning and deep learning models for language models and so the word embeddings and like word transformers, all those things. You just gave a detailed discussion on all these things. Hello?
Yeah. Hello. I'm there.
Thank you for that.
Thank you.
Thank you for the detailed lecture. So it's really kind of a very detailed explanation, I would say. So thank you for that. On behalf of the organizing committee, I thank all the participants for joining this webinar. I hope this webinar served its purpose. We are extremely thankful for our chairman, Dr. Rao Rataya, who always motivates us to organize these kinds of events very frequently. I thank Dr. M.Y.S. Prasad, Honorable Vice Chancellor, Dr. Raghunathan, Registrar, for providing enough support in organizing this event. And I would like to extend my special thanks to the speaker of the day, Dr. SOWMYA S. Sundaram, for giving a very detailed discussion on NLP and its applications. So I thank our HOD, Dr. D. Venkateslu, for his support in organizing the event. So once again, I thank all the participants for attending this webinar. So it would be helpful for us if you share your feedback. So people are sharing their feedback in the chat box. I think they are a little nervous to share with you. A very good, I think you can check that out.
Thank you so much for the comments, and thank you for the opportunity to come and share what I've learned. And it's very interesting to have such a session, especially in this time of lockdown where we barely have any such forum to discuss. And it was very nice. Thank you so much.
Thank you. So I have shared the feedback link in the chat box, so you can give your feedback. So those who already registered, who attended, and who give the feedback. So on successful submission of the feedback alone, those alone will receive the certificates. Okay. Thank you. Thank you for attending the talk. Thank you, SOWMYA ma'am. Thank you.
Thank you.
Thank you all. Yeah. Well, I hope I'll see you in upcoming webinars also. Sir, HOD sir, would you like to speak a few words about the webinar?
Yes, madam. So thank you very much, Dr. Soumya, for giving very interesting talk on natural language processing and its applications. So I'm sure that some of our faculty members really understood the various the applications of natural language process NLP, and also the potential applications of NLP in future. So we are very much grateful to you for accepting our invitation and joining this call during this COVID-19 period. Thank you very much. Hope to see you. Yeah.
Thank you, sir.
Yeah, thank you.
Thank you for sharing your words. So thank you, one and all. I'm closing this session. So people are now sharing their feedback. Thank you. Thank you all.
Thank you.
Thank you, SOWMYA. Once again, thank you very much.
Yeah. Thank you.
We'll see you later. Bye.
Yeah.
I'm closing the session.
Just speak.
Yeah, please. I'll share you actually. You can take this screenshot.
Yeah. Oh, you mean on the laptop itself?
Yeah.
Okay. Yeah.
All of you can, open your videos so that we can have a big
photo. Yeah.
Yeah. So whoever is available online, so at least you people can open your videos so that we can take a photo. So please open your videos. I would like to see your faces.
Hello, madam.
Yeah. Hello, sir.
The video cannot be opened by my side. I think it is.
Why? No. No. Everyone else opened. So most of them they opened.
It's showing you cannot start your video because the host has disabled it.
I did not actually.
Yeah, okay, then no problem.
All the other participants are able to open. So rest of you, can you please open your videos? So we would like to take pictures, screenshots of them. Yeah. Yeah, that's really wonderful to see all of you.
I took one.
Yeah. Good. So yeah, I think most of the people here in this screen they open.
Yeah.
Yeah, thank you all. Nice to see all of you here. Thank you. Have a great day. Bye.
Yeah. Thank you so much.